Awesome. It looks like everyone's in, so we'll go ahead and get started. Thank you for joining us for our 7th week of the Catalysis webinar. This week, I'll introduce our speaker, John Newman, who's from Physical Electronics. To introduce myself and the webinar, my name is Lorianne Schultz, and we also have on here Katie Slavinska. We're from the American Vacuum Society at the University of Central Florida. The way that the webinar will work is John Newman will give a 30 to 45 minute talk, and then if you have questions at any time during his talk, go ahead and just type them into the chat box, and I'll collect those and ask them to Mr. Newman at the end of his presentation. And I'm really excited to introduce today's speaker, John Newman, who completed his master's degree in analytical chemistry at the University of Minnesota in 1984, and since that time has specialized in the use of advanced surface analysis tools for the analysis of materials covering a wide variety of applications. John started his career in 1983 with Physical Electronics, a manufacturer of surface analytical instruments located in Eden Prairie, Minnesota, where he worked on the applications of Auger XPS and SIM techniques. During his career, John has toggled between 2 companies, Physical Electronics and Evans Analytical, always being involved in materials characterization and problem solving using surface analysis instruments. John is currently the Director of Analytical Laboratory at Physical Electronics USA. And today he's going to share an introduction to X-ray photoelectron spectroscopy, fundamentals, and applications. So I'll pass this on to you for whenever you're ready.
Okay, are you seeing my screen?
Yep, that's perfect.
Excellent. Okay. Well, thanks for joining everyone today. As Lorianne mentioned, the title of my talk is X-ray photoelectron spectroscopy, fundamentals and applications. I'm the director of the Analytical Lab here at Physical Electronics. And as an agenda today, I'd like to talk just a few slides about physical electronics, or PHY as we're nicknamed. And then I'll go into XPS, looking at the history of the technique, some of the basics. We'll look at the instrumentation that's used, and then the types of XPS data that you can obtain from the technique. We'll look at different ion beam technologies that can be used for depth profiling or surface cleaning, and then look at a series of different applications. So a little bit about physical electronics. So PHY is the world leader of surface analytical tools. We specialize in XPS, including hard X-ray XPS, Auger electron spectroscopy, or AES, and time-of-flight secondary ion mass spectrometry, or TOF-SIMS. And there's a picture here of 5 of our instruments that we currently sell, 5 of the most popular ones. We've been around for over 50 years now. We just had our anniversary, 50-year anniversary last year. The company was started by two gentlemen, Roland Weber in the left here, and then Paul Palmberg in the right. And they were out of the University of Minnesota here in just 20 minutes away from here. And they were in the EE department. And there's a picture of the instrument that they used for their studies here on the left. It's a glass instrument. And so to get a sample in and out, you had to literally break the vacuum, or I'm sorry, break the glass, put your sample in or exchange samples, and then seal up the glass then again. And so in order to get a sample in and pump down with diffusion pumps and start your analysis, you were probably looking at 2 or 3 days. Nowadays, we are a little bit better set up, where we have instruments that have rapid insertion probes or robotic arms on them, and you can get your samples in there in 5 minutes or so, and so it's much, much faster. We've come a long way in 50 years. We have 2 different locations, or 2 different headquarters. One is at a company called Ulvac PHY in Chigasaki, Japan, and that's where the manufacturing of the instruments is done. They handle all the sales and marketing and service for all of Asia, and they have a sales demonstration and applications lab there, as well as a large R&D department for hardware and software, and about 140 employees. They're housed in Ulvac Corporation, which you can see a picture here, a huge corporation in Japan. Physical Electronics USA is the other headquarters, and we're in Chanhassen, Minnesota. We handle all the sales and marketing and service for everything outside of Asia. We're similar setup. We have a sales demonstration and applications lab, but we also have a contract analysis lab to run samples for customers if they don't want to buy an instrument, or at least not right now. And we have about 90 employees. Here's a photo of the production floor at ULVAC Phi, and it's a very impressive site where they have dozens of different instruments being made on it at various stages in their assembly. And this is only about half of the production site, so it's a pretty impressive facility they have there. So the history of XPS, it dates back to the late 1800s, and that's when the photoelectric effect was first observed by Heinrich Hertz. But it really wasn't until the 1960s when Kai Sigmon's group at the University of Uppsala in Sweden really developed the instrument concepts and showed that XPS could be a useful analytical tool. And he referred to the name, or coined the term, ESCA for the technique, electron spectroscopy for chemical analysis. But since there's other techniques, that electron spectroscopy techniques that can be used for chemical analysis, most people use the term XPS, or X-ray photoelectron spectroscopy today. Sigbon is considered the modern day father of XPS. Now, about that same time, physical electronics was founded, and so we were kind of in the thick of things as well. And in 1981, Sigbon actually got the Nobel Prize for his work. The history of XPS at Phi is almost 50 years old as well. You can see in the upper left the original XPS instruments that were developed, the 548. No computer on it. It was all analog. Took quite a while to get samples in and out. And that's actually the instrument that I used in graduate school back in the early 80s. So I've seen the whole range of instruments as they've progressed over the years. So it's been kind of fun. Now, of course, there's better optics, more automation, and everything's digital, of course. So the basics of XPS. We'll look at the characteristics of the technique, and then a little bit about the theory and how we quantify the technique. XPS provides chemical bonding information. That's the main reason why people use it, and we'll get more into that in a little bit here. It's a very surface-sensitive technique, looking at the top 5 to 10 nanometers on a solid surface. You can get very good quantification. It's an ultra-high vacuum technique, so base pressures are 10 to the minus 10 torr range. It's a very good vacuum. Detection limits are typically in the tenths of a percent, atomic percent, but for some species that have very good cross sections, you can get down to about 100 parts per million. You can detect all elements above helium. And one of the nice things about XPS is that you can look at both inorganic as well as organic materials, and conductors as well as non-conductors. Yeah. What is XPS, and what kind of information can it provide? Well, XPS is an ultra-high vacuum-based system, as I mentioned. It's surface-sensitive, that uses soft X-rays to bombard a sample surface, and you can obtain localized, short-range bonding chemistries of elements on solid surfaces. So what do we really mean by this short-range bonding chemistry? Well, I'll explain that in terms of giving you some examples. So if there's sulfur present on a sample surface, is it present as a sulfide, or maybe as a sulfate or a sulfite? If there's fluorine present, is it a fluorocarbon or a metal fluoride? If platinum or some other metal is present, is it oxidized or is it in a metallic state? What's the oxidation state of copper? Is it cupric or cuprous or metallic, or a mixture of the two or three? If there's silicon there, is it present as a silicone or a silicate? It's very good at looking at chromium in terms of trivalent versus hexavalent state. And for the polymer industry and organics, it can discern different carbon chemistries. Is it present as carbide or hydrocarbon, or is it oxidized carbon present in various states? Or could there be some other elements that carbon is bound to? So it's these types of questions that XPS is good at answering. So you're looking at the local bonding chemistry of specific elements. The theory is pretty simple. We bombard a sample with soft X-rays, typically aluminum K-alpha at 1487 electron volts. And a core level electron is emitted from the sample surface, and we can measure the kinetic energy of that photoelectron. And since we know the X-ray energy and the kinetic energy of the photoelectron, we can determine its binding energy, how much energy it was being held in its orbital by the nucleus. And by determining that, we can tell what element it is and something about its chemistry. Here's an example of an XPS survey spectrum overlaid on the electronic orbital for cadmium. And you can see for each of the different orbitals where we have electrons present, we get peaks present. Now, if you were to take this cadmium and bond a electronegative species to it, like oxygen, that draws some of the valence electrons away from cadmium, and that in turn causes a shift in the binding energy of the core level electrons as they're being held in by the nucleus. And so you can monitor these subtle shifts in the binding energy of the different peaks. Luckily, a lot of the work has already been done, and you can find it in literature or in databases for the binding energy shifts that you get for different chemistries. Here's an example of a table of carbon chemistries. And you can see that the binding energy ranges all the way from 281 electron volts all the way up to 293, depending on what elements the carbon is bound to. And on the right, you can see an example of 3 different polymers that are overlaid on top of each other. One is polystyrene, where there's, in the red here, where there's only hydrocarbon present. The blue is polyethylene terephthalic, where there are 3 different chemical states for carbon present. And the green here is Teflon, CF2 bonding. And you can see that very easily separate out the different shifts. So I mentioned it's a very surface sensitive technique. Now the X-rays that we're using are soft X-rays, but they still penetrate microns into the sample surface. So the fact that it's surface sensitive isn't dictated by the penetration depth of the X-rays. But it really has to do with the fact that the electrons that we're monitoring are very low energy electrons, 1500 electron volts or less. And they can only escape without losing energy from the top several atomic layers. Now electrons can be emitted from below those layers, but they wind up losing energy on their way out, and they're simply added to the background, and they're no longer characteristic of the elements from which they came. Our surface sensitivity of 5 to 10 nanometers comes from, it's equal to 3 times the inelastic mean free path of photoelectrons, or lambda as it's referred to. And the inelastic mean free path is simply the distance that an electron can travel in a solid before it loses some amount of energy. Here's a representation of the depth of analysis of XPS compared to a few other techniques, and also its excitation volume. And you can see that XPS and Auger and TOF SIMS are all very surface sensitive, looking at the top 10 nanometers or less, compared to, say, Raman or EDS or FTIR, where you're typically looking a micron or more in depth. EDS, you can use lower energies and reduce that depth of analysis, but it's still nowhere near 10 nanometers. Now you can see that XPS has a much larger excitation volume or spot size than Auger or TOF SIMS. So why would you want a larger spot size? Well, in general, you don't want one, but this table explains why XPS is such an important technique. Its beam size is a couple orders of magnitude larger than in TOF SIMS, but it's about 3 orders of magnitude larger than it is in Auger. But it's the fact that you can get this short-range chemical bonding information, and you can get organic information from polymers and other organics. You have excellent quantification, and you can easily analyze insulators. That makes XPS such an important technique. If you compare it to Auger, the amount of chemical information you can get from Auger is very limited, and you really can't do organic analysis because the electron beam is damaging to organics. And it's difficult to do insulators with Auger. You can easily do insulators and get organic information from TOF SIMS and get really good molecular information, but you really can't quantify what you get in TOF sims. And you need standards, but that's almost impossible when you're looking at a monolayer of a surface. How do we go about quantification in XPS? Well, it's relatively complicated, and there's a lot of factors that go into it, but the intensity that we get for a certain peak is related to its concentration in the sample, N here, along with a whole bunch of other factors. Now, many of these factors under a given set of analytical conditions are constant, and others can be lumped into what we call a sensitivity factor. And so we can simplify this, again, if we keep our analysis constant, analysis conditions. So the intensity we get for a peak is equal to its concentration times the sensitivity factor. And so if we want an atomic fraction for an element on a surface relative to everything else that's there, we simply divide its intensity by its sensitivity factor, and all of that is divided by the summation of all the intensities for the elements we find on the surface divided by their sensitivity factors. And of course, all of this is done by a computer now, and so we really don't have to worry about doing any manual calculations. XPS instrumentation. All XPS instruments nowadays use monochromatic X-ray sources, typically aluminum K alpha. And they start with an electron source of some type that bombards an aluminum anode, and that generates X-rays. These X-rays are diffracted off a monochromator and go onto the sample surface, or diffract onto the sample surface. There, the photoelectrons and Auger electrons and secondary electrons are extracted with an input lens to an energy analyzer, where the energies are filtered and separated. And then you strike some type of detector for counting the number of electrons. There are really two flavors for XPS instruments. Some are microprobe instruments, and others are flood source instruments. The microprobes use a relatively small X-ray spot, and then you can use open lens analyzers to collect as much signal as possible. So it's the X-ray beam that defines your area of analysis. In the flood source, you use a very large flood of X-rays, and then you use apertures in your analyzer to restrict your area of analysis. Phi uses the microprobe type of instrumentation. And in fact, we've added a twist to it where we have a patented technology where we can raster the electron beam on the X-ray anode, and that in turn rasters the X-rays on the sample surface. That allows us to get X-ray induced secondary electron images like an SEM, and so we can operate the instrument like an SEM EDS does. And you get these images that show you the features on the sample surface and whether they're defects or pads or whatnot. And then you can simply pick points in the software on these images, different points of analysis, and without moving the stage, essentially acquire 3 points simultaneously, as shown here. In fact, you can do the same with depth profiles, where you can obtain multiple points of analysis in a single sputter crater. Being able to do insulators is very important in XPS, and the reason that it can be challenging is that when you bombard a sample with X-rays, it causes a localized positive charge. And because the sample is insulating, it doesn't have a way of neutralizing that charge. In general, people use low energy electron floods to try to neutralize that charge, but in some instances, the sample surface has a negative potential on it, kind of a static charge, and that causes a deflection of the electrons that are trying to reach this area of analysis, but they can't because of that static charge on the surface. So at Phi, we use a very low energy flood gun as well to flood a positive charge on the sample surface, and that then allows the electrons from the electron flood to reach this area of analysis and nicely neutralize the surface. The energy of the electrons is typically only about 1 eV, and the energy of the ions only about 5 to 10 eV. So very low energies. Other pieces of hardware that are important, say for the catalysis industry, are things like glove boxes. where you want to do your experiments within a glove box and then transfer the sample without exposing to air through some type of chamber into the main analysis chamber. And that's pretty common with several of our customers. So now let's look at the type of XPS data that you can obtain. There are multiple different types of data. The first are what we refer to as survey spectra, and these are scans over relatively large energy ranges, typically over 1,000 eV, and they're used to determine what elements are present, and you can't quantify the data from the surveys as well. The analysis or the analyzer conditions that are used under high sensitivity mode, which means relatively low energy, but we're primarily trying to figure out what elements are present. We can then run high resolution scans, or narrow scans as they're called, on the elements of interest. And these are typically only about 15 to 20 electron volts in width. And these allow us to look at the subtle shifts that occur, giving us the chemical state information that we're looking for. We run the analyzer in a high energy resolution mode in these instances, so the transmission is less, but we get much narrower peaks. We can also do compositional depth profiles where we can follow species with depth. And you can do that in a couple different ways. One is with ion sputtering, where you combine XPS analysis with ion beam sputter etching. And so you take data with XPS and then you sputter a little bit, and you take data and sputter, take data, sputter, and so on and so forth. And you can change your ion beam settings to sputter as much as you want, much or as little as you want, whether it be 5 angstroms removed in a sputter cycle or 500 angstroms removed in a sputter cycle. Typically, most depth profiles are done less than a micron in depth, just because the deeper you go, the more artifacts that can occur in terms of sample damage or roughening of the surface. And sample damage is something that you do have to consider when doing depth profiles, because ion beams can alter the chemistry of the sample as it's sputtering. Now, the other way that you can do depth profiles is what's referred to as an angle-dependent or angle-resolved mode. And this is used to look at composition with depth, but without ion sputtering, and also with only the top 1 to 10 nanometers of the sample surface. And you do this simply by changing the tilt of the sample relative to the analyzer, and that can vary our depth of analysis. And I'll show an example of that shortly here. We can also obtain photoelectron maps with XPS, and that's used to look at the lateral distribution in X and Y of elements on the sample surface. You can also obtain line scans, which are similar to maps, but just in one direction. So this is what, on the left here, we have a survey spectrum of polyethylene terephthalate, or PET. Those are the pop bottles and water bottles that we're used to drinking out of. And that tells us what elements are present, and we can quantify from this simply by integrating the peaks. In this case, we have carbon and oxygen present. If we now take high resolution scans on the carbon, we get the spectrum over here on the right. And we see that the carbon is present in multiple peaks, and these are all carbon peaks, but they're due to the different, or the peak shifts are due to the different chemistries that are present in PET. The carbon-carbon peak, or carbon-hydrogen peak that we get here at 284.8 is indicative of the aromatic ring, the 6 carbons in the ring for PET. The CO functionality is from the ethylene groups, where these carbons are attached to, singly bound to oxygen. And then we have the carboxylate groups as well that show up as a different peak. And the ratio of carbons is 6 to 2 to 2, and that's roughly what we get for quantification in this case. We also see a subtle peak here that's indicative of the aromaticity of the PET ring. So these are the high resolution scans are the really important ones where we determine what chemistry is going on, but first we need the survey spectra to tell us what elements are present. Here's an example of a depth profile. This was of an architectural glass coating on glass. And we see that we have concentration versus sputter depth here on our sputter depth on the x-axis. And we follow different elements with time as we sputter below the sample surface. And we have a series of different layers here and we can see sharp interfaces. Some of these layers are only about 10 nanometers thick, so we have very good depth of resolution as we depth profile into the films. We monitor the different elements and their binding energy with depth. In this case, we have aluminum doped silicon oxide on the outermost surface, and we get a certain binding energy for that, the silicon in that chemistry. At the interface of the glass, we actually see a shift down to what appears to be a silicon nitride coming from a reaction of the titanium nitride on top of the glass. And then we have the silicon from the glass itself. Here's an example of a angle-dependent depth profile. We mentioned earlier that our depth of analysis is equal to 3 lambda, lambda being the inelastic mean free path. And it's actually 3 lambda times the sine of what we call the takeoff angle, which is the sample surface relative to the analyzer. And our maximum depth of analysis is when the sample surface is perpendicular to the analyzer. Now, if we simply tilt the sample away from the analyzer, the photoelectrons that get into the analyzer have to traverse across the sample. And so even though you're still looking at 3 lambda here, your effective depth of analysis is modified by the sine of that takeoff angle, in this case 10 degrees. And so you're really changing your depth of analysis to about 17% of your maximum depth of analysis when you're at a 90-degree takeoff angle. We have some spectra here on the right that show different data sets coming from an SiO2 on silicon sample, just a native oxide on silicon. And at a grazing angle, or 20 degree, we see roughly similar intensities for the metallic peak at about 100 electron volts versus surface oxide at about 103.5. And as we go to more normal takeoff angles, like 75 degrees here, we see that the intensity for the elemental silicon is much higher than the oxide, because now we're going through the oxide and analyzing well into the silicon substrate. Here's an example of a hydrocarbon layer, contamination layer on top of silicon oxide, on top of silicon substrate, silicon metal substrate or metalloid. And you have atomic concentration versus sine at the takeoff angle, with the data on the left-hand side, or the low sine takeoff angle numbers, being more surface-sensitive data, and the deeper depth of analysis is over on the right side of the plots. At the low takeoff angle, we see that there's a lot of carbon present, as there should be since it's a hydrocarbon contaminated surface. And we see almost or over 40% carbon. But then as we look more normal at deeper depths of analysis, we see that the carbon drops off to just a few percent. We see that the silicon metal, that's the substrate, is 0 on the sample surface, but it increases in intensity as we go to deeper depths of analysis. The oxide is kind of in between, where it's kind of humped here, the silicon oxide peak and the oxygen peak, as it should be, since the silicon oxide is buried between the hydrocarbon and the silicon substrate. So again, the angle-dependent mode is good for looking at the top 10 nanometers or less. I mentioned you could obtain elemental maps with XPS. Here's an example of a fluorocarbon contaminant on a PET substrate. And you can map for fluorine and carbon and easily see that the fluorine is primarily present in the fluorocarbon contaminant, whereas we have carbon everywhere, although there's more present off of the fluorocarbon contaminant than there is on that contaminant. That was elemental mapping. You can also do chemical state mapping. On the upper left here, we have a yellow image of a silicon map. And in each pixel of the map, you have a complete spectrum of silicon. And you can look at, after the fact, look at different regions and see that there are different chemistries present in this silicon map. We have an oxide present in the bright yellow. In the dark center here, we have a silicide. I believe it's a tungsten silicide. And around that silicide, there's a thin oxynitride layer. And we can use mathematical routines like linear least squares fitting to separate out these chemistries for the oxide, the nitride, and the silicide. So at Phi, we have 3 different ion beams for different applications, for either depth profiling or for cleaning of a sample surface. There's monatomic argon, which is just single atoms of argon that are bombarding a sample. And these have been around for decades, argon beams. And these are best for looking at metals or semiconductors or metal oxides in depth profiling with a very good depth resolution. However, you really can't depth profile or sputter clean organic materials because the monatomic argon rapidly damages the organic material. Over the last 10 to 15 years, cluster beams have been developed for depth profiling applications. C60 was the first to be developed, and seen here are buckyballs, as some of you might remember. And that's good for profiling some organics without any chemical state damage. Also for looking at inorganic oxides with better stoichiometry than monatomic argon sometimes. And also really good for looking at mixed organic, inorganic materials. So for example, some of the organometallic catalysts that are used, the C60 I'm guessing would probably be best for those applications. And then we have these huge argon gas cluster beams that can be generated. And these are best for looking at organic, pretty much all organic materials. Because as you sputter into them with these large beams, it retains the chemical state information that we're looking for. It sputters organic materials hundreds of times faster than inorganics, so it works very nicely for just cleaning organics off of inorganic samples. So depending on the application, we'll use different ion beams or a mix of ion beams as the case may be. So let's look at some applications for XPS now. In general, XPS is, of course, we're looking at chemical bonding information in many cases. Sometimes we're just using maybe the surface sensitivity for look for elements present. Most of the time, it's chemical state information. We're looking at oxidation state and oxide thicknesses of metals and alloys. We can use it for characterizations of stains and discolorations and regions of corrosion. It's very good for looking at powders and residues. We use it for the evaluation of cleaning processes when you want to change from one cleaning process to another. This is especially important if you want to see if your new cleaning process that maybe has gentler chemicals in it, is that working as well as the old ones? We often use it for looking at carbon functionality of polymers and other organics. Say, for example, if you're plasma or corona modifying a sample surface, how much oxygen are you incorporating into that organic surface? Very good for looking at adhesion issues. We mentioned depth profiling of thin films for composition or diffusion or contamination. Uniformity of thin coatings, if you want to see if a coating is present in large area, relatively large areas, covering centimeters or so in size. And often used for competitive analysis. So company A wants to see what company B is doing in terms of their products and vice versa. Over the years, we've looked at pretty much anything you can get into a vacuum system in XPS. Everything from looking at computer disks and read-write heads to fruit flies and teeth, moon rocks and dental floss and lipstick and anything, again, you can get in there. Even the kitchen sink, we literally have analyzed the kitchen sink. Here's an example of, we talked earlier about using glove boxes. You can also use glove boxes that aren't attached to the XPS instruments, but then use some type of transfer vessel, as shown here in the lower left, to transfer from the glove box into the XPS chamber. And you can see here an example of you analyzing lithium metal with the transfer vessel. You see a large peak in XPS for lithium metal and smaller ones for oxides and hydroxides or carbonates. Now, if we did the same experiment without using the transfer vessel, and on that same lithium plate, all you see is lithium carbonate, which is a common reaction that occurs when lithium is exposed to air. Here's an example of looking at an iron catalyst on a carbon support. And in the as received state, the iron is primarily present as iron oxide, Fe2O3 it appears to be. With a small amount of metal, we're also picking up at about 707 electron volts. Now we did some hydrogen experiments with flowing hydrogen at 500 C for 30 minutes, and you can see that a fair amount of the oxide has been converted now to iron metal. If we up the temperature to 600 and increase the hydrogen flow, we see that now we have primarily iron metal present and the oxide peak is much, much smaller. Here's an example that I found in the literature recently, just this last year, where they're looking at titanium dioxide and what happens with temperature. And so the red line here is TiO2 at room temperature, and then you can see as you increase the temperature from 300 to 500, the intensity for the titanium in the +4 state decreases, and you can see an increase in lower binding energy for titanium 3+. I have to apologize here. The binding energy in this particular paper that was published is backwards, and so it goes from low to high, which traditionally it goes just the opposite in XPS spectra. But you can see here the change in the chemistry with temperature. Here's an example of studying boron in graphene. And at room temperature in the carbon spectrum, you see that there's a graphene peak here, that's the main peak, but you also see some oxidized and nitrogen-containing species present at higher binding energy. And in the nitrogen spectrum, you do see the presence of the nitrogen. You have roughly half and half of boron carbide and boron oxide present at room temperature. And now as you increase the temperature, you remove the nitrogen and those oxygen and nitrogen containing contaminants that were present on the graphene. So you have a simple single carbon peak now for graphene. And you've also slightly changed the amount of the ratio of carbide to oxide. But when you go to 800 degrees, you see that you formed much more of the boron carbide and less of the boron oxide present. And you can see that in the boron chemicals narrow energy scale spectra here. Here's an example of a study done on alumina-supported silver catalyst, where we compared a fresh catalyst to an aged catalyst. And interestingly enough, you see in the fresh catalyst there's about 18% silver, while the silver drops dramatically down to about 2.6% after aging. And the aluminum from the substrate or the support goes from 17 to 27%. Well, at first glance, it appears that somehow the silver is disappearing or diffusing into the bulk or something else. But we did some Auger analysis on this, and I'll show you that in a second here. We also found many other different elements present on the sample surface. Some of these are other catalysts that are added besides the silver. Some are promoters, some are contaminants. But for proprietary reasons, we can't show those here. But here's the Auger data that shows some maps for silver and aluminum and cesium, actually, for the fresh catalyst as well as the aged catalyst. And at the top, you see the SEM images. And on a fresh catalyst, all the silver that was present was in extremely small, I guess they were 0.05 to 0.1 micron size silver particles. After aging, you see that the silver particles have agglomerated into roughly 1 micron size. So in XPS, since you're looking at large areas, and because now the majority of the sample surface is not covered in silver like it is on a fresh catalyst, you see a reduction in the amount of silver present in XPS. So that explains why it goes from 17% down to 2%. You also see that there's a shift in the silver chemistry between the fresh and the aged catalyst, where we're going from metallic silver to oxidized silver after aging. Here's an example of a platinum catalyst on a carbon support. XPS uses primarily carbon, but with lower amounts of oxygen, chlorine, platinum, and sulfur. If we look at the platinum chemistry, we see in the as impregnated catalyst, it looks dramatically different from the activated catalyst. Doing some curve fits and looking at the peak positions to tell chemistry, we can see that it's primarily either chloride or hydroxide on the as impregnated catalyst, while the platinum is metallic in the activated catalyst. So in summary, XPS is excellent at providing localized chemical bonding information. That's its main claim to fame. It's a surface-sensitive technique with accurate quantification. Detection limits typically in the tenths of a percent. You can detect all elements above helium. You can look at both organic as well as inorganic materials, as well as conductors and non-conductors. In this presentation, we've included some information if you want to look more into databases that are present or application notes on our website or practical guides for doing XPS. We have a whole variety of different resources listed here. One other side note is that for analyzing catalysts that are often in a powder material, we like to use just simple double-sided tape, and we support our local 3M here in Minnesota. And so this particular permanent double-sided tape, as it's called, is real good. It's very sticky, and so the catalyst stays put on the tape very nicely. It has no detectable silicone, which can be a problem with many tapes. And so it's nice for that, and it works very well with these powders, whether they're in chunky form or very finely powderized. I'd like to acknowledge our XPS team here for helping me with all the data they've provided: Jenny Mann, Ben Schmidt, Lisa Schwartz, and Katerina Archer-Skova. And with that, I would like to end and be happy to take questions.
Thank you so much for that excellent talk. Thank you. I do have the list of questions here for you. Firstly, would you mind commenting on why the analyzer has a hemispherical shape?
Yes, that's to bend the electrons towards the detector. And so if you have a voltage on the inner sphere and the outer sphere of the hemisphere, and it's only those electrons that have the proper energy that are bent at just the right amount to strike the detector. Those electrons that have too high or too low of energy will hit either the outer sphere or the inner sphere and be neutralized. And so it's just a way of separating out energies once they come off of the sample surface.
That makes sense. Thank you. Are there any alternative methods that provide similar results that XPS does, such as oxidation charges of an element?
Yes, there are none that are really surface sensitive, as XPS. Auger, in some cases, can give chemical state information, but it's relatively limited, the number of elements that it can provide chemical information for. X-ray diffraction actually can give positive identification for chemical bonding or chemical species, say whether it's Fe2O3 or Fe3O4 for iron, for example. However, the material has to be crystalline for X-ray diffraction. Raman can actually give some chemical state information as well. So there are multiple techniques, but XPS is the best for looking at the outermost atomic layers.
Awesome, thank you. Could XPS be used to find a coordination number of different facets of copper metal in atomic arrangements?
Coordination number, that would be interesting. It may be possible, but it would probably be required to have a set of standards where you have different coordination number reference materials and analyze those first. But we'd have to look at the specific details of the experiment and the samples that you'd like to look at to see if it would be feasible.
Thank you. How do you account for changes in the relative selectivity factor for angle-dependent analysis?
relative selectivity. I guess I'm not quite sure what
I
you
think
mean by
that
that.
accounts for the size of your area that you're scanning for, so
Ah,
different
okay,
change.
okay. Yes, it does. When you have a microprobe type of sample, or I'm sorry, system, it does elongate the X-ray beam on the sample surface. Um, this, of course, will only work when you have homogeneous surfaces. We're assuming that if you elongate the beam, you're still getting the same chemical state information.
Thank you. Is there an advantage of using XPS mapping over EDS mapping?
Again, the surface sensitivity is going to be much improved in XPS versus EDS. Where in EDS, you're typically looking a micron or deeper, depending on your beam voltage, whereas in XPS, you're looking at the top few atomic layers. The beam size for XPS is going to be quite a bit larger than it is for EDS. However, depending on your conditions of your electron gun in EDS, the excitation volume can actually be very similar to what it is in XPS.
Thanks. For the treatment of signal, how important is the value of formula width half maximum? Can we modify this value at all?
I'm sorry.
Sorry, yeah, I'll repeat it. For the treatment of signal, how important is the value of the full width half maximum? Can we modify this value?
Well, the full width half max is used for looking at some things like if you're looking at the beam size or if you're looking at the width of a layer in a film. But in general, what we do is we integrate the whole peak for quantification purposes anyway. And so in that instance, we don't use full width half max. It can definitely vary. Different people, I would say, or different scientists use different methods of looking at the narrowness of the peak. But yeah, that full width half max is the way that most people use it.
Thank you. Is there a recent reference that you could recommend for the use of DFT methods for the calculation of XPS spectra for solid state materials?
That would be a good question for one of our other scientists here, Katerina. Will we be getting copies of all the questions that we can answer them?
I can email this person that
Okay.
you give that to me.
Okay, all right. It might be that something like a CESA database might be appropriate, or Quasys is another one.
Okay, thank you. For titanium 3+ and titanium 4+ example, does temperature affect the efficiency of emitting a photoelectron in its peak specific manner? For example, is the difference a temperature artifact versus a change in chemistry?
Well, there could be some efficiency difference. We haven't, I guess, personally done enough studies to know if there is a slight change there. However, we did see the lower binding energy peak increase in intensity. So it might actually be a couple different factors going on there, but the fact that you do see the +3 state increase in intensity, at least according to this particular study that I referenced there, they attributed that to the actual chemical change in state.
Thank you. Does Phi have a plan to redesign the system for a high pressure XPS at all?
Nothing imminent.
Okay. And is it possible to quantify subsurface species such as oxygen in the case of noble metals by XPS?
So if you have a noble metal oxide, in terms of quantifying that?
Yeah, I believe.
Yeah, as soon as you start depth profiling, you have to be careful because reduction of metal oxides is a common problem with monatomic argon sputtering. And so what would be best to do is to have a reference where you know it has a certain stoichiometry,
Mhm.
and you could check that by RBS or a technique like that. Then depth profile it and see what your steady state levels of oxygen and metal are, and then do the unknown and see if you get that same ratio.
Thank you. Could you elaborate on the usage of near ambient XPS for probing mechanism of catalysis?
To tell you the truth, we at Physical Electronics, we really aren't in the near ambient XPS game, so to speak.
Mhm.
We followed that, and we see that there are a lot of studies that are being done. We've heard some comments that the pressures available in the near ambient XPS instruments are not what they are in real life or real usage.
Mhm.
And so they may not be as applicable as people would like them to be, but that's about all that I guess we know about.
Thank you. What is the spatial resolution that can be achieved with XPS imaging?
It varies among the different vendors of XPS. It can go for some of the techniques where they use what is referred to as parallel imaging. They
Mhm.
have modes that they can get down to, say, 1 to 3 microns. Um, our particular system, where we spec it at 7.5 microns, in reality, probably around 5 microns, but it's in that 1 to 5 micron regime where XPS spots are, at least for laboratory-based systems. It can be smaller for synchrotron radiation or some specialized systems, but the majority of them are in the micron regime.
Thank you. One last question. What is the impact of using charge compensation with a sample that is not an insulator?
If you float the sample like with the tape that I showed you there from 3M, you'll get identical results with or without the neutralization, whether you have it grounded versus floating it with an insulator. The one thing you don't want to do is ground it and use a charge neutralizer, because then if there's any insulating region on that particular sample, you may get some differential charging occurring.
I see.
In general, looking at a conductor with charge neutralization, as long as it's floating, will be fine, because the whole surface potential is constant.
Thank you. Thank you so much. I'll just share 2 final slides for everyone. Thank you again so much, John Newman, for taking the time to present this. So many questions, so I'm sure it's extremely helpful. Thank you for your excellent lecture.